All right, here are 4 exercises to test your comprehension of the probability theory that we've covered so far. The first one is, what is the probability of drawing the ace of spades twice in a row? And in order to do that, let's assume that any card drawn on the first draw will be put back in the deck before the second draw. In the second exercise, you draw a card from a deck of cards. After, again, replacing that drawn card back in the deck and shuffling thoroughly, what is the probability of drawing the exact same card again? For exercise 3, use the n-choose-k formula to calculate the probability of throwing 3 heads in 5 coin tosses. And then finally, for exercise 4, create a Python function that solves exercise 3 and incorporates the n-choose-k formula. With that method in hand, with that function in hand, calculate the probability of, in 5 tosses, throwing each of 0, 1, 2, 3, 4, and 5 heads. Okay, so for the probability of drawing the ace of spades twice in a row, well, assuming that we're putting the card back in the deck, which is what I specified in the question, then we have the same probability twice. So we've got the probability of drawing the ace of spades, which is 1 in 52, and then to get the overall probability, we multiply that by the probability of it happening again. So 1 in 52 times 1 in 52, because there's only one card from amongst the 52 in the deck for each case. Multiplying these two by each other, that gives us with 1 in 2,704, which is approximately a 0.04% chance. So the probability is 0.00037. Very unlikely to draw 2 aces of spades in a row. All right, exercise 2 was a little bit of a trick question. You might not have expected this. So the question was, what's the probability of drawing a card and then drawing that same card again? So the probability of drawing any card is 52 and 52. There's a 100% chance that you will draw some card on the first draw. So really the only probability that matters is, what are the odds of drawing that same card again? Well, whatever the card was, on the second draw, we have a 1 in 52 chance of drawing that specific card again. So if you drew the ace of spades on that first one, the odds of doing that again are 1 in 52. And so we multiply these two probabilities by each other. 1 times 1 in 52 leaves us with 1 in 52. And so that's your probability. That converts to about 2%, 0.019. Okay, for exercise 3 here, first I'd like to point out that while I did properly indicate these are solutions 1, 2, and 3, GitHub doesn't render those solutions properly in this statically viewed notebook. There are other options for viewing, which we'll go over shortly, and for working along interactively with all of the code examples in these live lessons. We're going to talk about that in the next video, but for now, just trust me that this is the solution to exercise number 3. So working with our n-choose-k formula, we're interested in a situation where we have 5 coin tosses, n equals 5, and from those 5 coin tosses, we get 3 heads, so k is equal to 3. Then we can just substitute the values into our formula, which we worked through already earlier, our n-choose-k formula, which is one of the key terms that I definitely recommend you know for moving forward with probability theory. So we can drop our values in there. We've got n factorial in the numerator, so 5 factorial in the numerator, and then in the denominator, we drop in 5 for wherever n was, and 3 for wherever k was. So simplifying a little bit, we have 5 factorial divided by 3 factorial times 5 minus 3, which is equal to 2 factorial. And then multiplying that out, the 5 factorial on the top is 5 times 4 times 3 times 2 times 1. And then in the bottom here, we have the 3 factorial and the 2 factorial. I don't think I need to read those out for you. So simplifying these, this numerator factorial comes out to 120. So 5 factorial is equal to 120. 3 factorial is equal to 6, and 2 factorial is equal to 2. Multiply 6 times 2 gives us 12, and 120 divided by 12 is equal to 10. So overall, all of this work that we've done here with this n choose k, that gives us the numerator for the probability of the event happening, of getting 3 heads. So the probability of our event, so there's 10 outcomes where we have 3 heads. And now all we need is the denominator. So how big is our sample set? How big is omega? Well, we know from an earlier video that for a coin toss, we can use 2 to the power of n, where n is the number of coin tosses that we have. Again, that's that same number 5 as here. So 2 to the power of 5 is equal to 32, which means that there's a 10 in 32 chance that we'll get 3 head flips in 5 coin tosses. And that corresponds to a probability of 0.3125. Nice. So the task for exercise 4 is to encode the solution to exercise 3 in Python code. So I imported the factorial method from the math library, and then I created a function. You can call it whatever you'd like. I called it coinFlipProb for coin flip probability. And into it, I pass the 2 arguments n and k. So the first thing that I do inside my coin flip probability method is I calculate n choose k. So I encode this n choose k formula here. So I have factorial n in the numerator, and then in the denominator, I have factorial k times factorial n minus k. And so that gives me my n choose k, that gives me my numerator. And then to get the final coin flip probability, I'm going to have that numerator, n choose k, divided by 2 to the power of n. So once you have your function that you built for calculating coin flip probabilities, then you can iterate over all of the possible outcomes. So we're always going to have 5 coin tosses in the exercise that I asked for, and then we're iterating over 0, 1, 2, 3, 4, and 5 heads tosses from the 5 coin flips. So we're varying the value of k, the number of heads that we get. So the probability of getting 0 heads in 5 coin flips is about 3%. The probability of getting 1 head in 5 coin flips is about 16%. The probability of getting 2 or 3 heads is 31% in either case. The probability of getting 4 is the same as the probability of getting 1, which is about 16%. And finally, the probability of getting 5 heads is the same as getting none, which is about 3%. Cool. Hope you enjoyed those exercises. Up next, we're going to dig into some hands-on code demos for the first time together, talking about the law of large numbers and the gambler's fallacy.